this video, we're going to discuss vertical projectiles. It's just when you throw a ball straight up into the air. So it can't move across, just up or down. We'll also introduce the relationship between weight and mass, and we'll make a transition from doing motion graphs and start using equations of motion. Quick warm-up question for you. Pause the video, try the question, come back for the answer. So in part A, it's gaining 10 meters per second of speed every second. So after 1 second, be going 10, after 2 seconds, 20, after 3 seconds, 30 meters per second. Part B, average speed. Well, it started out with a speed of 0 meters per second, and it increased its speed at that constant rate, 10 meters per second every second, until it reached 30 meters per second. So because it was increasing at a constant rate, the average speed should just be in the middle of 0 and 30. It should be 15 meters per second. Part C, how far will it travel? Well, how far it travels will equal that average speed times the amount of time it traveled. So that would be 15 meters per second average speed for 3 seconds, giving you a grand total distance of 45 meters. Part D, a VT graph. Well, after 1 second, it'll be going 10, after 2 seconds, 20, after 3 seconds, 30, and it's going to increase its speed at a linear rate. So you're going to get a straight line with a slope equal to 10 meters per second every second. In our warm-up exercise, I chose an acceleration of 10 meters per second every second because the most common acceleration of all is approximately 10 meters per second every second. That's the acceleration due to gravity, which we usually represent with a small letter g, is equal to about 9.81 meters per second every second. Or we often round that to one significant digit to get 10 meters per second every second. And all objects that are dropped, regardless of mass, accelerate at 9.81 meters per second every second. You might find that a little bit weird. You might think heavier objects accelerate downwards. They fall quicker than lighter objects. You might not trust this cartoon physics here with the elephant and the mouse, that they're going to hit the ground at the same time. But what you can do is take a sheet of paper and take a book and drop them. And yes, the book's going to hit the ground first. But then what you do is you take your piece of paper, fold it in half if it's a big piece of paper, and put it on top of the book. Then drop them together. And you'll find that they stay together. They accelerate downwards at the same rate. And that's because the book is blocking out the air resistance. So we do need to add a little qualifier to our statement here that all objects that are dropped, regardless of mass, accelerate at 9.8 meters per second squared. We need to add in there, in the absence of air resistance. And if you don't believe it, watch this video with Brian Cox of the BBC. He's dropping a feather and a cannonball in the world's largest evacuated chamber, where there is no air resistance. Watch what happens. So why is it that all objects, regardless of mass, in the absence of air resistance, have the same acceleration? Well, here we've got a big mass, capital M. Here we've got a little mass, little m. And the obvious thing we can say here is that the big mass is going to have a bigger gravitational force on it. And the little mass is going to have a smaller gravitational force. But that's not the end of the story. Because when you got more mass, it also means you've got more matter. And things that have more matter, they're harder to push. They're harder to accelerate. And these two effects are going to kind of cancel each other out. Bigger gravitational force, but more matter to pull. Smaller gravitational force, but less matter to pull. And in fact, when we learn Newton's second law, we'll find out that acceleration is equal to the ratio of force to mass. And the gravitational force acting on the big mass will be equal to its weight. And its weight is given by its mass times the acceleration due to gravity, that number 9.81. Our little mass, gravitational force on it, is given by its weight, which is given by its little mass times the acceleration due to gravity. So if we compare the accelerations, for the big mass, we've got its weight as a force divided by its big mass. And for the little mass, we've got its weight, little m times g, divided by its little mass. Naturally, the masses cancel out, and we get that A equals to G regardless of mass. So because the ratio of weight to mass is the same for all objects, they all get the same acceleration. So we were saying that gravitational force is equal to mass times this acceleration due to gravity. And we've got another name for gravitational force. Usually we just call it the weight. So weight is equal to mass times g. Well, weight or forces, the SI units for force are the newtons. The SI units for mass are kilograms. So it's kind of a mistake when you say, my weight is 65 kilograms. That's really your mass. Your mass is 65 kilograms. And the units for an acceleration, the acceleration due to gravity, are meters per second squared. But sometimes this g gets another name. So it really goes by two names. When we talk about it in meters per second and squared, that would be the acceleration due to gravity. But a meter per second squared is equivalent to a newton per kilogram. And when we write it as a newton per kilogram, we give it a different name. We actually call it the gravitational field strength. Now, these two units are equivalent to one another. When we talk about it as gravitational field strength, we're talking about how many newtons of gravitational force act on each kilogram of mass. So we have two representations. And where students often go wrong is they confuse weight and mass. And the key difference between weight and mass, weight depends on where you are. Well, if you're on the surface of the Earth, your weight is always about 10 times as big as your mass. You're multiplying by 9.8. But on the moon, the gravitational force, your weight on the moon would be a lot less. So your weight or the gravitational force, it depends on location. If you're at the top of Mount Everest, the gravitational field is a little less than 9.81. It's about 9.78. So your weight on the top of Mount Everest is a little bit less. Weight depends on location and is a force. But mass only depends on the amount of matter. It doesn't depend on where that matter is located. So your mass is going to be proportional to the number of electrons, protons, and neutrons in your body. And you can kind of neglect the electrons because they have a lot less mass than the protons and neutrons. So this mass is proportional to the number of protons plus neutrons. We have a collective name for that. A proton or neutron is called a nucleon. So it's proportional to the number of nucleons in your body. And g here, we can think of it simply as a proportionality constant between mass and weight, but we're probably best off thinking of it in terms of the gravitational field strength. So that the gravitational field strength at the surface of the Earth is 9.8 newtons acting on every kilogram, whereas on the moon, the gravitational field strength is weaker. There's only 1.7 newtons of gravitational force per every kilogram of mass located on the surface of the moon. Quick question for you. Pause the video, give it a go, come back for the answer. Let's consider the mass first. Well, mass is the same. The amount of matter, the number of protons and neutrons in that person, would be the same whether he's on the moon or on the Earth, so it's 70 kilograms in both cases. When we're talking weight, though, it's different. On the Earth, we'd say that the weight was equal to the mass, 70 kilograms, times the acceleration due to gravity on the Earth, which should be that 9.8 newtons per kilogram, which is 690 newtons. However, if the man is on the moon, the gravitational force acting his weight is going to be less. It will be equal to 70 times 1.7, giving you a weight on the moon of about 120 newtons to two significant figures. Second question, a little more conceptual this time. Pause the video, try the question, come back for the answer. The answer here is yes and no. Typically, your scales are reading in kilograms, and that's units of mass. And mass doesn't change anywhere in the universe. However, our scale is set up to measure gravitational force. It's really set up to measure weight. It's the gravitational force that squeezes that spring that gives you a reading on your scale. So mass should not change, so it's wrong. However, if your scales are set up in newtons, so that they're really set up to measure weight, then our 70 kilogram man would get readings of 690 newtons and 120 newtons, depending on whether they were on the Earth or on the moon. So set up in newtons, your scale would work. Now a spring could be used to measure mass. Heavier objects will oscillate on a spring with a slower frequency, and that frequency can be used to determine the mass. So we could use a spring, in fact, to measure mass and get the same value on the Earth as on the moon. Let's come back to our vertical projectiles. So we're going to imagine tossing a ball straight up at 20 meters per second. We're going to take g to be 10 meters per second every second, and we want to draw aligned position time, velocity time, and acceleration time graphs. We're going to start with the VT graph. We know we start with a positive velocity of 20 meters per second. Now the acceleration is in the opposite direction. So the acceleration is negative 10. That means you're going to subtract 10 meters per second of the speed in 1 second. So if this is our 1 second line, we should come down here to 10. And we'd continue that pattern down to 0 after 2 seconds. And continue that pattern still. This is where it's at the top of the path, 0 velocity. Loses another 10. Now it's going downwards with a velocity of negative 10 meters per second. And continues that pattern. We're just getting a straight line graph. Like so. The slope of that graph is equal to the acceleration, which is negative 10 meters per second every second. Which means we've got a constant value of negative 10 for the acceleration. That means our acceleration graph's going to be very easy to do. Here's negative 10. We just draw a straight horizontal line across at negative 10. Notice there that at the top of the path, the velocity is 0. The velocity is always changing, but the acceleration is constant. And that's important to realize, and it comes up often on IB exams. Now, let's consider the position. And I'm going to consider the first 1 second interval. It's decreasing its velocity at a constant rate. So the average velocity would be halfway in between 20 and 10. In other words, it'd be right here at 15 meters per second. And if you go at 15 meters per second for 1 second, you'll go 15 meters. So this should be at 15 meters after 1 second. Let's try the same game over the first 2 seconds. Average speed starts at 20, ends up at 0. Average speed would be 10 right here. Go at 10 meters per second for 2 seconds, and you'll go 20 meters. So it should be 20 meters up after 2 seconds. We can continue that process. Let's take this 1 second interval here between 0 and negative 10. Average speed would be negative 5. Do that for 1 second. You'd go negative 5 meters. In other words, you're going to come down 5 meters from that 20 meter height. And of course you're going to get a symmetrical curve here. I think most of you know the story. We get a parabola. Graphs are kind of hard to work with because it's hard to draw graphs all the time. Much easier to work with equations. So let's turn these graphs into equations. First one, we'll start with the acceleration time curve. We've just got an acceleration that's constant and is equal to the acceleration due to gravity. So for this particular graph, a is equal to -10, and in general, a will be equal to the negative value of the acceleration due to gravity. That negative value just means you're taking downwards to be negative. Second graph here, well, that's a straight line graph, so it has to have the general form y equals mx plus b. Let's substitute in our specific values. Our y variable is the instantaneous velocity v. Our slope, that's the -10. Our x variable is time. And our y-intercept is 20. Or we can write that in more general terms. We could say that the velocity will be equal to -gt plus the initial velocity. And let's do the same thing for our parabola up here. Now for our parabola, I'm going to go directly to a general equation and just show you that it works for this particular case. I'll leave the mathematics for math class. So as a general equation, our displacement would equal our initial displacement, I'll call that x naught, plus the initial speed, u, times t, plus 1/2 times the acceleration, the uniform acceleration for that particular problem, times t squared. Now in our particular case, our displacement is just going to be our height. Our initial displacement was 0. It started on the ground. Then we'd have an initial speed there of 20 times t, and our acceleration here was -10. So this would be 0 plus 20t minus 5t squared. So for instance, if I were to put in t equal to 2 seconds, I should be at the top of my path at 20 meters. So putting t equals 2 in, I get 20 times 2. That's 40 for this term. And this term would be 5 times 2 squared, or 5 times 4, which is 20. Subtract them, you do get 20, positive 20. So at 2 seconds, we get 20 meters. And you can check that at 1 second and 3 seconds, you get heights of 15 meters as well. So now let's try another example. This time we're not going to use any graphs. We're just going to use the equations or a bit of reasoning. And this time we're going to throw up our ball, our object, at 30 meters per second. Find out the velocity and height of the ball at 1 second intervals. Pause the video, try the question, come back for the answer. So for the velocities, we really don't need an equation at all. It starts with a upwards velocity of plus 30. And the acceleration is downward, so we've got to subtract off 10 meters per second of speed every second. So after 1 second, it would be going plus 20. After 2 seconds, plus 10. Down to 0, minus 10, minus 20, minus 30. If we were using an equation, we'd simply say that the velocity would equal the initial velocity minus 10 times t. So 30 minus 0, 30 minus 10, 30 minus 20, 30 minus 30, etc. Now for the heights, we could use a little bit of reasoning, or we could use our equation. I'm going to start with the reasoning method. Our velocity is changing at a constant rate, and the average velocity over the first 1 second time interval would be 25 meters per second. So if you go at 25 meters per second for 1 second, you should go a distance of 25 meters, and the ball should be 25 meters in the air. Over the first 2 seconds, the average speed would be halfway between 30 and 10. That would be 20. Go at 20 for 2 seconds, you should end up 40 meters above the ground. And we can continue that process. Average speed over the first 3 seconds would be 15. 15 times 3 would give you 45 meters. And you can continue that reasoning to get 40 meters, 25 meters. Of course, the average velocity would be 0 over the first 6 seconds, so it would come back to where it started. Or of course, you can use your equation. The height should be equal to that initial speed times time. In other words, this here represents how high the ball would have gone if there weren't any gravity. If gravity weren't pulling on it at all, it would have gone at constant speed and it would cover 30 meters per second every second. But of course, gravity is acting downwards and it's going to bring it down by a distance of 5t squared. So after, let's say, 4 seconds, we would have 30 times 4 minus 5 times 4 squared, which would be 120, minus 80, which is equal to 40 meters. Agreeing with our answer here. And one final IB question to finish off the video. Pause the video, read it over, make sure you understand it, see if you can do it or see how far you can get with it, and then come back for the answer. So let's start by writing down our equations for velocity and for height. So in general, our velocity is given by the initial velocity minus the acceleration due to gravity times time. So in this particular case, it's going to be 8.0 as the initial speed minus 10 times t. So that gives us the velocity at any time. And in general, our displacement will be given by an initial displacement plus the initial speed times time plus 1/2 at squared. Now in this case, our displacement is called the height, and we're going to measure the height from the top of the cliff. So the initial height is going to be 0 because we're measuring from the top of the cliff. The initial speed is going to be 8.0, and when we multiply by the time, we get how high it would have been if there weren't any gravity. But then, of course, gravity brings it down by 5t squared. So now the first thing we're asked for is the time to reach maximum height. And we know something about the velocity at maximum height. The velocity has to be 0 at maximum height. Right here, we've got an equation that tells us the velocity at any time. So let's set that velocity to 0 and see what time that has to occur at. I'll let you solve that. You should get t equals 0.8 seconds. So it's going to take 0.8 seconds for that ball to reach its maximum height somewhere over here. We're then asked for what is that maximum height? Well, we know the time, and this equation tells us the height at any time. So let's substitute in. The h should be equal to 8.0 times the time for maximum height, 0.8, minus 5 times 0.8 squared. And I'll let you work that out. It should come out to be 3.2 meters. So this height here would be 3.2 meters. And as I showed in the other picture, we're assuming that there's no height between the hand and the cliff, that distance there is negligible. And lastly, we're asked for the height of the cliff. So what we're going to try to do is figure out what's the height of the ball when it hits the sea. We know it takes 3 seconds to hit the sea. And our height is given by 8.0 times the time minus 5 times the time squared. So let's put in 3 seconds. 8.0 times 3 minus 5 times 3 squared. Work that out, you get 24 minus 45, which is equal to negative 21 meters. So on our diagram here, what that's saying is that the ball is 21 meters below where it was released. The height is measured from the top of the cliff. So the ball is going to be 21 meters below the cliff when it hits the water. And therefore the height of the cliff has to be 21 meters. Let's summarize the key ideas. Idea 1, A equals G for all objects regardless of mass if there's no air resistance. And if they're on the surface of the Earth, that value is going to be 9.81 meters per second squared. Idea 2 was that the weight is equal to the mass times gravity. The weight is in newtons, the mass is in kilograms, and this g here can either be thought of as the acceleration due to gravity, meters per second squared, or the gravitational field strength, the number of newtons of force acting per kilogram. The weight, it depends on location. Whereas the mass in kilograms does not depend on location. It's a measure of the amount of matter. And the third thing was really writing down these equations for a vertical projectile. The acceleration was kind of trivial. If we take g equal to 10, then the acceleration would simply be -10 all the time. The velocity will be given by the initial velocity, but then you've got to subtract off 10 every second. And then the height of our projectile would be given by, well, any initial height, if it had some, plus how far it would go if there weren't any gravity. And then you've got to subtract off the effect of gravity, that 1/2 gt squared, or 5t squared, taking g equal to 10. And then we can use those equations together with knowing some of the physics, such as the fact that at max height, the velocity has to be 0. At that turnaround point where it's at maximum height, you're going to have 0 velocity. The acceleration is still -10, but the velocity will be 0. And that's all for today, folks. Thank you very much.